Welcome back. In the previous video we discussed how an AC power system is controlled. In this video we will discuss what this means for the integration of photovoltaics in an electricity grid. Fluctuations in the power output are an inherent problem of distributed generation. A large contribution of photovoltaic systems to power generation can cause easily power fluctuations in an electrical power system. As discussed in the previous video, this becomes a problem especially for the utility manager who must guarantee power to be transmitted to the different loads. In traditional power systems, the power is injected constantly by power plants into the grid, making management of the power generation according to the system load relatively simple. Now, with the widespread diffusion of distributed generation systems, grid management has become more complex. In fact, PV systems show a peak when the irradiance is at its maximum over the panels. This usually occurs in the central part of the day, while during the night the electricity provided is minimal and even close to zero. More in detail, due to the rapidly changing weather conditions, such as the presence of clouds, the output power is likely to vary on a second or minute basis. In this scenario, these short-term fluctuations can cause problems with the quality of the power that a load receives. Besides the primary and secondary control strategies discussed earlier in the previous video, some different approaches can be adopted to minimize the impact of power fluctuations. For example, by means of geographical dispersal, it is possible to have simultaneously connected to the grid two or more PV farms that receive different sun irradiance or that are subject to slightly different weather conditions that can affect power production. Moreover, if the fluctuations are characterized by a longer term, backup generation in the grid system is required in order to maintain the power supply. Another good way of managing intermittent power inputs into the grid is to forecast the probable PV production in selected areas. Meteorological data used by grid operations to make intensive use of forecasts to control the power flows and guarantee a constant feed to the loads. Nevertheless, a forecast could be lower than the actual power generating, having therefore more power than required by the grid. In this case, traditional power plants are shut off to avoid a surplus of energy in the system that could cause faults or could end in waste of power produced. Alternatively, this power in excess can be stored. On the other hand, the forecast might also be higher than the actual PV production. In this case, backup power generation is needed to cover the energy demand. It is clear that even though forecast algorithms could be very accurate, these are nonetheless affected by the unexpected weather conditions or problems in the distributed generators. Another way of coping with power fluctuation is the installation of big storage facilities. In this case, when the power output of the PV system is higher than the demand, the excess can be stored to be then reused when necessary. Battery systems are characterized by very fast response times. So next to the storage of renewable electricity, batteries can have an additional functionalities of helping to stabilize the electricity grid. Fluctuations in the power output can cause transients in the power supply, which will affect the quality of the power. These transients decrease the power factor, which is defined as the ratio between the real power, active power P, and the apparent power S. The apparent power is the sum of the active power P and the reactive power Q. The beer mug analogy is a very common and intuitive way to explain the effects of power factor on the electricity grid. Let's suppose the beer is the real power in watts, while the froth on top of it represents the reactive power, VAR, voltage ampere reactive. As seen before, the sum is called apparent power in VA. Although a customer pays only for the beer, he will receive also some undesired fraud that will occupy the space in the mark, thus decreasing the quantity of beer received. The analogy also suggests that the mark must be sized in order to contain both the beer and the fraud, just like cables and other system components must size considering both active and reactive power. We must then take into account that only real power can be transmitted and then used by the load. Therefore, a poor power factor on the grid increases line losses and makes voltage regulations more difficult. In order to regulate the reactive power present in the system, changes to the software control can enable many inverters to supply positive or negative reactive power to the grid during voltage dips or rises. As mentioned earlier, in order to avoid problems with functioning of the load, frequencies must be uniform throughout an interconnected grid. Therefore, to summarize this part, disruptions in the balance between supply and demand lead to frequency fluctuations. In particular, the frequency of a system falls when demand exceeds supply. The other way around, frequency rises when supply exceeds demand. Harmonic content must also be taken into account when analyzing the high penetration of PV power on the grid. Harmonics are spectra with integer frequency, multiples of the fundamental power frequency. Let's consider the voltage output waveforms of a PV inverter working in a square wave mode. The red square wave can be approximated by the sum of an arbitrary number of sinusoidal waves by means of Fourier series. The first harmonic or fundamental is a pure sinusoid, and it is the one carrying active power. Nevertheless, also superior harmonics are present and are injected into the system, contributing to the harmonic distortion of the signal. All electrical appliances and generators produce harmonics and are therefore regulated under standards. In large volumes, these harmonics can add up, causing interference, malfunctioning of devices, and even fires. In order to reduce the harmonic content, filters can be used. Filters use capacitances and inductances either in parallel or in series to cancel out the lower or higher harmonics from the output power. Apart from passive filter circuits, some more expensive active harmonic filters can be used. The PV array provides through the inverter a square wave signal. This signal can be divided into fundamental wave and harmonic waves. An active filter injects into the grid a harmonic compensation wave that evens out the distortion. This way, a filtered wave can be delivered to the grid. Another challenge that electricity grids are currently facing is the fact that due to the energy transition, the need for electricity as energy carrier is rapidly increasing. Many sectors are replacing fossil fuel power technologies by electrified technologies. So look at the electricity grid in the Netherlands. Here you see the electricity demand per month in the Netherlands for the year 2015. Let's assume that a part of the residential heating should be replaced by electrical powered heat pumps. Currently, it's mainly based on gas powered heating. This would impact the electricity demands in the cold winter months. Light blue indicates the extra electricity energy needed for heating. In addition, if a large part of the passenger cars would be replaced by electrical cars, this would add an additional electricity need indicated in the light yellow. Note that these are just back of the envelope estimates I have added to these graphs. Nevertheless, this figure implies that the capacity of the electricity grid in winter months would need to significantly grow in this example by almost 50%. This also implies that this extra electricity should be generated by renewable electricity like wind and solar electricity. In the last 10 years, the total installed PV capacity, for instance in the Netherlands, has increased from only 0.8 gigawatts in 2030 to 17 gigawatts in 2022. Per capita, the Netherlands has the most PV power installed within Europe. This enormous growth has also posed a challenge for the electricity grid. The timescale to install a large-scale utility PV farm is faster than the timescale to locally increase the capacity of the electricity grid. Here you can see the map of the Netherlands. In the not-colored regions, the electricity grid has transport capacity available to connect a new large-scale utility solar farm to the grid. In the yellow-colored regions, the electricity grid has limited transport capacity available to connect a new large-scale utility solar farm to the grid. In the orange-colored regions, the electricity grid has provisional no transport capacity available anymore to connect a large-scale utility solar farm to the grid. And in the red-colored regions, the electricity grid has for the time being no transport capacity available anymore to connect a large-scale utility solar farm to the grid. This shows that many regions, the expansion of the electricity grid cannot keep up with the increased integration of photovoltaics. It demonstrates that the energy transition needs an integral approach to facilitate the growth of the electricity generation, the transmission, storage and consumption of electricity. In summary, in the last two videos we have discussed some challenges for the integration of photovoltaics into the electricity grid. We briefly touched upon topics like power and frequency control approaches of the electricity grids in general. Based on these principles, I hope you have started to create some understanding of the potential impact of large-scale integration of PV in the electricity grid in terms of the power and frequency management, forecasting approaches, harmonics and fast increasing share of the PV in the energy system. With this video we conclude week 2. We now know which components are included in a PV system. In week 3 we are going to design a PV system, so see you back in the next video lectures.